The Technical AI Safety Podcast is supported by the Center for Enabling Effective Altruist Learning and Research, or CLR. CLR, known to some as the EA Hotel, is a nonprofit focused on alleviating bottlenecks to desk work in the effective altruist community. Learn more at CLR.org. That's CEEALAR.org. I wanted my first few episodes to be about the intersection between formal methods and reinforcement learning. In order to do that, we're going to do a brief overview of what reinforcement learning is. It's not meant to teach you it if you don't know it. It's just meant to jog your memory if you maybe learned some of it at some point and you need to review. So I've prepared a brief kind of intro to what reinforcement learning is, so hopefully we can jump in. Reinforcement learning, or RL, is a subfield of artificial intelligence responsible for advances in Go playing and self-driving cars. It starts with the notion of agent that is concerned with maximizing reward signals within a suitable representation of the environment called a Markov decision process, or an MDP. To think about MDPs, start with something like automata. The world is carved into states, and the state you're in is governed by some transition function with respect to actions. Then, add in the element of randomness to create probabilistic transition functions. Finally, incorporate reward signals associated with each state or each state action pair. An algorithm for learning how to maximize reward in this environment falls under the umbrella of reinforcement learning. To this end, many concepts are leveraged, such as discount rates, future reward is worth less than present reward due to exponentiating a hyperparameter gamma, policies, tables, probabilistic or deterministic, that tell you what action to take depending on what state you find yourself in, value functions, various means of estimating the expected value of finding yourself in a state, and many, many more. If you want to get started, check out University of Alberta's Coursera specialization on reinforcement learning. We're going to be jumping right in the deep end of this episode, and you might not be able to get up to speed just by listening to this intro. So if you have to set this episode aside while you learn the basics, we understand. Bettina Könighofer works as a postdoc at Graz University of Technology in the Secure and Correct System Group. Her research interests include synthesis, verification, bridging the gaps between formal methods and AI, logic, and applications to security. Ruediger Ehlers is a professor for embedded systems at Clausthal University of Technology in Germany. He works on formal verifications and safety assurance of machine-learned models, as well as synthesizing correct by construction systems. Safe reinforcement learning via shielding. Abstract. Reinforcement learning algorithms discover policies that maximize reward, but do not necessarily guarantee safety during learning or execution phases. We introduce a new approach to learn optimal policies while enforcing properties expressed in temporal logic. To this end, given the temporal logic specification that is to be obeyed by the learning system, we propose to synthesize a reactive system called a shield. The shield is introduced in the traditional learning process in two alternative ways, depending on the location at which the shield is implemented. In the first one, the shield acts each time the learning agent is about to make a decision and provides a list of safe actions. In the second way, the shield is introduced after the learning agent. The shield monitors the actions from the learner and corrects them only if the chosen action causes a violation of the specification. We discuss which requirements a shield must meet to preserve the convergence guarantees of the learner. Finally, we demonstrate the versatility of our approach on several challenging reinforcement learning scenarios. Safe Reinforcement Learning via Shielding was published on the 3rd of September in 2017 by Mohammed Alshiekh, Roderick Bloem, Ruediger Ehlers, Bettina Könighofer, Scott Niekum, and Ufuk Topcu. So, welcome listeners to the first episode of the Technical AI Safety Podcast. I have with me doctors Bettina Könighofer and Ruediger Ehlers, who are going to talk about the paper Safe Reinforcement Learning via Shielding. So, thanks for coming on the show, y'all.
Thanks for inviting us.
So first, just take us through the abstract. You're going to tell us about shields. So what are shields?
So Bettina, do you want to take that one?
Yes. The shield is basically a small monitor that you put after your reinforcement learning agent. So the shield monitors the environment and the actions of the agent. And whenever the agent wants to do something that is unsafe, so it wants to send an unsafe action to the environment, it just overrides the unsafe action with a safe one. So the cool thing is that we don't implement the shield by hand, that we have given a model of the environment dynamics and a formal safety specification, and we automatically synthesize the shields. And by doing that, we have a correct by construction guarantee so that we know that the shield is correct. So if you attach it to the learning agent, the entire setting gets correct. And then you can really prove that your learning setting always adheres to the safety critical specification. Never, something bad can never happen if you do that.
Fantastic. I'm assuming we have an artificial intelligence audience. What does correct by construction mean?
It means that you synthesize your system automatically, you never implement it. So by constructing the system, you already know that it will satisfy the specification. So there's no need for debugging, there's no need for testing. You know that the system that you get will satisfy the specification. So you have a proof you have already proven that the system satisfies the spec.
Awesome. Great. So what was the status quo of reinforcement learning way back in 2017 when this paper was written? And why did you feel like you needed to write this paper?
Bettina, should I take this one?
Yes.
Okay, so in 2017, there was a lot of talk about using AI in a safe way. That means if you want to apply techniques such as reinforcement learning in safety critical contexts, then it wasn't so 100% clear how exactly to do this. So since we both, and also our co-authors, come from the formal methods domain, of course, to us, the question of how to make systems more safe was kind of natural. So we felt that there was a need to bring these two communities together. And for this reason, we started this work where we integrate ideas from reinforcement learning and from formal methods. And we were hoping that we could essentially integrate the correctness guarantees that formal methods give you into the performance and convergence guarantees that reinforcement learning gives you. And I think this worked. This is how I would sum up the paper in a way.
Awesome. Rüdiger, do you want to add words on what formal methods are for reinforcement learning audience?
Yeah, so in formal methods, the question is always, how do you prove that a system that you're having is correct? So it all boils down to getting something like, a mathematical proof that shows in a step-by-step fashion that whatever you're dealing with really does what it's supposed to be doing. Now, there are two ways of doing so. First, you can build a system and then prove that it's correct, or you can take the specification of the system you're trying to build that you should have anyway if you really want your system to be correct, and try to automatically generate a system implementation from the specification. Now, in formal methods, the question is, how do you make this happen? So first of all, how do you specify what a system should be doing, which is already pretty difficult on its own. And secondly, there's the algorithmic question of how do you prove a system to be correct, or how you can generate correct by construction systems. And since all of these problems are so difficult, this is a whole research community, that tries to improve the state of the art in a step-by-step fashion to really get modern, embedded systems and also software systems safe and correct by construction.
Awesome. Well, that sounds like it would be really important for artificial intelligence.
Well, we hope so, at least.
Yeah. When I think of a when I think of a proof, I'm thinking about you know, maybe some kind of like inductive proof about like even numbers or like the infinitude of the primes, where the proposition generates proof obligations and you pursue a proof in like a very specific way. Like what I'm getting at is the proof obligations aren't jumping around on you. But in artificial intelligence, the environment is often probabilistic. Um, so how does like the demand of a proof respond to dealing with probabilities in an artificial intelligence environment?
So I think, Bettina, you want to take this one because it also goes into the direction of the second paper that you co-authored with Niels.
I can try to. So first of all, I think formal methods covers a lot of areas like model checking, verification, theory improving, synthesis, and so on. So because I think you ask several things at once in your question. Because of course we're also doing things like natural deductions and so on, and depending in what area you are, a proof will mean something different in formal methods. So in this work that we have here, we are really considering deterministic settings, where we say, okay, we play a safety game, and our proof is then basically also a deterministic strategy, where you say, okay, if you're in this state, these and these actions are safe, and these actions are for sure safe. In future work, we extended this in several directions. One of them is also to consider the probabilistic settings, where you say, okay, we shield an MTP, and we say, we guarantee you that the probability that you reach an uncertain state is lower than some certain threshold. So this is what we did in future work together with Niels Janssen. But in this work, we really say, we guarantee you that no matter what happens, there will never be something unsafe. Of course, this is not always realistic. For example, if you now say if autonomous driving, you can't never guarantee safety for sure, because the other one can just drive into you and then you have a problem. And you would need probabilistic guarantees. But we didn't do this in this paper.
Okay. So in your related work section, you defined safety and reinforcement learning as follows. Quote, an exploration process is called safe if no undesirable states are ever visited, which can only be achieved through the incorporation of external knowledge, unquote. What is meant by external knowledge, and how do we know that the non-visitation of undesirable states is dependent on it?
So, Bettina, can I take this one?
Yeah, sure.
Okay, thanks a lot. So let's assume that we have an agent that tries to learn something, and the agent really has no clue about the environment, and there's something that this agent shouldn't be doing in this environment. The agent basically has no information whatsoever that could be used to prevent doing this undesirable thing. So, for example, I don't know, if a human baby starts to make its first tries at moving around, basically things will break, because how is this human baby supposed to know when things are going to break? And in the field of AI safety, there's often the same problem. There are certain things that an agent should not be doing, but there's no a priori knowledge that the agent has that would allow the agent, not to do these bad things. So what now has to happen is that if we're trying to use an AI agent in a safety critical context, then this normally means that we know what exactly this means. What is this thing that the agent should not be doing? And this has to be captured in one way or the other. And this is this external knowledge that is so important, at least to us, for making a system safe.
Okay. So let's start like diving into the meat of the paper. Could you please take us through what a reactive system is?
So traditionally, when we think about software, we think of a piece of code that does something and then terminates. So for instance, if we're trying to sort a couple of numbers, then we have a piece of software that will sort these numbers and then it will terminate because it's done. Now, a reactive system is a different type of, well, computational system. So in every step of its execution, it does a computation and produces output. And it will do that for eternity. And the best example is probably a traffic light because everyone knows it. And secondly, it does not terminate. If a traffic light runs today and nobody stops it, it will still run tomorrow and perform its computation. And the main difference between a reactive system and a terminating piece of software is when you reason about correctness. Reason about what happens after the system is done. You have to reason about the temporal behavior of such a system over time.
I see. Very good. So what's a specification and when is a specification realizable?
Bettina, I think you want to take this one.
Okay, thanks. A specification tells you what your system should do. So not how, but what. So for example, you can say, I want to go from, so I am in Graz and Rüdiger is in Clausthal, right? I want to go from Graz to Clausthal. This is what I want to do. And then you could give this specification to the synthesis tool, and the synthesis tool would tell you how you can go from Graz to Clausthal. Would tell you, take the train, take the bus, do whatever. So it's often easier to just define what you want like a system to do instead of how it should do it. And if this is the case, then reactive synthesis makes sense. Then you specify what you want to have, give it to a synthesis tool, and you automatically get your correct by construction system that satisfies your spec.
What is temporal logic?
Sure. In our paper, we use the safety fragment of LTL in order to define our safety properties, in order to write our specification. And the safety specification basically tells you all of the bad things that should never happen. Invariant properties, like, for example, Rüdiger's traffic light example, where we say it should never happen that both roads have the green light at the same time. So these are very simple invariant properties, but you can also have more complex properties that talk about time. Such, for example, you could say at the crossing, if there's a car, it is never allowed that this car is waiting for more than 30 seconds. And then you can, of course, require things that are not realizable. For example, you could say, okay, you have this traffic light controller, and every car should get immediately the green light if there's a car waiting. You can realize this if it's also required that both roads are not allowed to have the green light at the same time. So if you write a specification, you have to be careful that there still systems exist that can realize your specification.
I see. So how does the safety fragment of linear temporal logic relate to temporal logic?
So in LTL, you can express more property than safety properties. You can also express liveness and fairness properties. So LTL extends propositional logic by temporal operators, like always, eventually, next. What did I forget? Until. And with these operators, you can formulate liveness properties like eventually, infinitely often, something good should happen. But we don't consider these properties in our paper. We only concern about the safety properties because these are exactly the properties that we want to enforce with our shields. Because all of the performance objectives are optimized by the learning agent, and the shield is only there to override the actions if it's absolutely necessary in order to ensure safety, and that's why we only consider the safety fragment of the LTL.
I see. Okay, that sounds like a really powerful tool, and this is something that like you found in formal methods, right? Like,
yes, it's very typical in formal methods that you specify the properties that a system should have in temporal logic, and then you can also check your hardware that already exists and check if your hardware satisfies certain properties expressed in LTL, and use model checking and verification techniques to do so.
Cool. So I'm going to pull another quote here. A specification is called a safety specification if every word that is not in the language represented by the specification has a prefix, such that all words starting with the prefix are also not in the language, unquote. So I was just wondering if you could review for us how words relate to MDPs.
Rüdiger?
Yeah, okay, I take that one. Words here are just a formal definition, but they relate to executions that you can see in an MDP. So the basic idea is that in an MDP, you have a couple of states. And these states tell you something about, well, the state of the system you're observing. But they don't tell you anything about the history of how the system evolved over time. And this is something that you quite often need when using temporal logic specifications. Bettina just mentioned an example that I think is a pretty nice one. So at a traffic light, every car should get a green light after at most 30 seconds. Now, a system may violate the specification, but we can't figure this out by just looking at individual states. And the words here should really represent the evolution of the system, and by looking at it, we can figure out if this property is violated or not. And this is something that is quite fundamental when you're trying to enforce temporal specifications for a learning agent, which could, for example, work using an MDP model. If you want to enforce such a temporal property, then looking at the MDP states alone is not sufficient. But rather, you need to restructure the MDP in a way such that enough of the history of the execution in the MDP is maintained to figure out whether such a property is satisfied or not.
Okay. All right, that makes sense. Okay, so I have another quote. For specifications in LTL, it is known how to check if it is a safety language and how to compute a safety automaton that represents it, unquote. So what are the performance constraints on this ability?
Yeah, that's a very interesting question, because there are several views on how to answer it. So when putting the complexity theory hat on, the answer is it's really difficult to check if a linear temporal logic specification is a safety specification or not. But in practice, it's relatively simple, because most specifications that you're dealing with are really short, and hence the high complexity of this problem is not a big deal in practice at all. So what we are seeing in most of the works in the area of formal methods is that it's relatively easy to check if a property is safety or not by using the standard methods that we use in formal methods, by translating it to an automaton, and then just analyzing the structure of this automaton to figure it out.
But at this point, I'm curious about the games and safety games, and how they arose as a way to sort of automate this process of finding safety specifications and finding and like ensuring adherence to those specifications. So what's the deal with games and safety games?
Yeah, I think this is a very important part of the paper, because this is very typical for our community, but I don't think that this is so common in the reinforcement learning community that people know about this. So one way to automatically synthesize systems is by solving a game. So this is kind of relates to the games that you have in mind, because we always also say that we have a good player and a bad players. So we have a two-player game. And we say the environment is the bad player, and we, the system, are the good player. And we pick turns. So the environment picks the inputs, and the system picks the outputs. So in each turn, you play a game by environment picks inputs, system picks outputs. And the goal of the system is to satisfy the specification. And the goal of the environment is to violate the spec.
Right.
And by solving the game, we mean that we find a strategy for the system that it is always able to pick the output in such a way that it will always win. So if you find such a winning strategy, then you basically can guarantee that for any inputs that the environment could ever give, you will always win, so you will always satisfy the spec. And if you have such a strategy, well, then you have a system that is provably correct for whatever will happen. And this is what you want to have.
Fantastic. So we're assuming that like the opponent, the environment, is going to play like the worst case moves.
Exactly. That's how you get the absolute guarantees. Because for the worst possible inputs that the environment can give you, the evil player, the good player, the system will play in such a way that the spec will always be satisfied. So you say you have to avoid also all things where you can still avoid falling off the cliff. And this is what you get by playing the game. You really plan ahead that you will also not enter a state from which the environment can force you into something bad. You also avoid all of these states. And this is what you're doing when solving the game. Do all of the states where you can always be sure that your play will stay in the safe region. And this is why we call it a safety game.
Fantastic. All right, so I want to try to explain what we've gotten so far to see if I'm really grokking it. We have reactive systems, which are non-terminating computational processes. And there's a formal definition, but we're not at that level. We're at like a higher level. A specification is some description of what to do, and a realizable specification is one that we can synthesize. We can synthesize a how to do it from the description of what to do. We use linear temporal logic, which is a logic with temporal operators such as next and until, or globally, or what the linear temporal logic operators are. And that's how you describe specifications. And what that does is it takes words, which are basically runs through the MDP or like execution paths, and the specification checks if that word is essentially safe. And you can model this as a game between the system and the environment. Did I butcher it too bad? How was that?
No, that sounded excellent.
All right. Then we're on the same page. So let's continue then. What's with the need to develop approximations, or you call them abstractions, of MDPs?
Bettina, I think I take that one, okay?
Yeah, this one.
Yeah, so first of all, there's a reason why we call it an abstraction and not an approximation. Because if you use approximations, you normally quantify how much wrong your model is. Now, we call it an abstraction because the abstraction we're building is 100% correct. So it's not wrong at all. So we already talked about the problem for a learning agent to figure out what it's allowed to do and what it's not allowed to do without any prior knowledge. It basically can't do so, so we have to encode somehow what a learning agent is allowed to do. And the idea here was that we use a standard technique, again, from formal methods. where you're modeling an environment in which a system that is supposed to work correctly operating in. And this is also called an abstraction of the environment in the field of formal methods. So we stick to that term. And the basic idea is that you kind of need to capture the behavior of the environment in which the learning agent should operate. So for instance, if you want to learn an agent that steers a vehicle through a maze, well, then you need to roughly capture the vehicle dynamics, because whatever you want to express in terms of keeping the system safe, it needs to be relative to the dynamics of the car. If the car has a lot of inertia, then there are probably other actions that the agent can do than if the car can come to a standstill almost immediately. So an abstraction covers all of these aspects, and it needs to be fully correct. And this is basically where the imprecision of the whole approach comes from. So since we come from this mindset that the system has to be 100% correct, but we are willing to sacrifice some performance for this correctness, an abstraction should cover all of the possible behavior of the environment that we can see at runtime, and it is allowed to cover a bit too much. We are trying to control, has to take into consideration that certain things could happen in the environment and they must not happen. Then it has to behave a little bit conservatively. And what exactly that means is covered in this idea of an abstraction.
I see. It's excellent.
So perhaps allow me to add one thing, if that's okay at this point.
Yeah.
One of the main difficulties is that when performing game solving, as we need to do, in order to guarantee that the system will always behave safely, at least with the current approaches for game solving, we need to work with finite environments. However, if you think about controlling a vehicle, that is not a finite environment. There are infinitely many different positions at which the vehicle can be. So the core difficulty is really breaking down this infinite number of states of the environment in which the agent works to a finite number of states. And of course, we have to lose precision along the way. And this is why it's also called an abstraction. Mm-hmm. It doesn't really represent the real thing, but just enough to work on it.
Right. So this is different from, like, in standard reinforcement learning, where the MDP is, this might be POMDPs, I'm not sure, but partially observable MDPs, but the thing where the environment is not observed all at once, and like the agent builds up like a cache of the environment over time. This isn't like that at all. This is still like taking the whole environment as input at once and then computing the abstraction. Is it like that, or does it work?
Yes, it's exactly like that. But I need to make a very small addition. We don't need to know at 100% precision how exactly the environment behaves. We can basically add safety margins on the environment dynamics. And we can use these safety margins when computing these abstractions. And then what we're getting is still a way to make sure that the system behaves safely at runtime. But performance will degrade when the margin is too large.
I see. So in AI safety, we talk about competitiveness, where we don't want to live in a world where the safe way to train a model costs 10% more computing power than the unsafe way to train a model. So what we want is safe means of training to cost 10% less than unsafe means of training. And this idea is called competitiveness in some of the literature I've seen and some of the people I've talked to. It sounds like getting safety this way, it would be really difficult to make competitive methods, right? Like how would it cost more for Uber to implement this in their self-driving cars than it would cost for them to do something that's less safe.
No, I don't think so. I think this really depends on the setting. For example, if you have a platooning controller, so the learning agent should learn to control a platoon of car, it never has to explore all of the policies where the cars drive too close, because the shield would interfere and say, hey, now you're too close, this is dangerous, don't do that. So the learning agent has to explore fewer policies because it doesn't have to explore all of the unsafe ones, because the shield says no. I cannot guarantee that learning always gets faster, but in many experiences that we performed, also the learning performance increased when we added the shield.
Okay, fantastic. Yeah, I'll clear some space later on to talk about the experiments that were done. But for now, I want to get into the distinction between preemptive and post-pose shielding. You have two kinds of shielding in this paper. There's preemptive and there's post-posed. So what is going on there?
So in our paper, we distinguish between pre and post shields. So basically, we compute with the shield for each state the set of safe actions. And then you can decide if you put the shield in front of the learning agent or after the learning agent. If you put it in front of the learning agent, we call it the pre-shield. If you put it afterwards, we call it the post-shield. So if you have the post-shield, we say the learning agent monitors, the shield monitors the actions by the learning agent, and if the agent is unsafe, it overrides it with a safe one. Now you have to tell the learning agent which action was really executed, because it has to make a policy update. So if the action from the learning agent was executed, it's clear, then it updates its policy with that action and the reward. If the shield overrides the action with a different one, then you have to tell the learning agent that the different action was executed. So it can make two policy updates at once. So one for the action that was executed with the actual reward, and one for the action that is tested with some negative punishment. If you put the shield in front of the learning agent, we call it the pre-shield. And then the shield basically allows at each time set the set of safe actions. And if the learning agent only picks one of the safe actions, then we can have the correct setting.
I see. Okay. Is it sort of like case by case based on the problem at hand, what would be more effective?
It depends on what setting you have. So if you have a Q learning agent with a Q table, then you can just have the shield in front of the learning agent and block the unsafe actions. If you have a neural network, it might not be possible to really block actions. So this really depends on the setting that you have, or you would like to have it. Also, are you already done with training? If you are done, it probably makes more sense to have the shield afterwards and just override the actions. So this depends on the setting, and I still have the echo.
Okay, cool. So another important thing is the properties of correctness and minimum interference. So I think I know what these are. Minimum interference is just only interfere when you absolutely have to. The shield should only constrain the behavior of the agent in a dire circumstance. It shouldn't constrain the behavior of the agent without like a good reason to. And correctness, right? That's what minimum interference is. I believe, and correctness is, I don't know what correctness is. Am I right on minimum interference, and what is correctness?
So Bettina, should I take this one?
Yeah.
So you're absolutely right on minimum interference. It essentially means that the shield should only change the choice of action of an agent if it really has to. Now, correctness here means that shield and agent together will never do something that is violated by the specification.
Right.
So the system should, in a sense, always behave correctly, even while it is learning, and even if the agent is trying to do something that makes no sense and should be prevented.
Okay. So when you have the shield synthesis code, the code that takes the specification and synthesizes the shield as output, would you say that the output of this synthesis like naturally or for free enforces the two properties of correctness and minimum interference? Or does it take extra work to make sure the synthesis has those guarantees?
Well, it's the basic idea behind synthesis, that whatever you're generating automatically, it enforces correctness, and it always does so.
Yeah, so it's like it's really
And
for
minimum
free. It's natural.
Yes, so it's for free in terms of the execution of the system. Now, it should be stated, however, that the shield has to be stored somewhere, and it can have quite a good number of states. So if you implement your learning agent in an embedded system, you should still take this into account, that you need some extra memory for the shield.
Mm-hmm.
So it's not for free in that sense, but for free in the execution sense.
Got it. All right, so I want to ask about, there was a remark that I believe Bettina made about training earlier, and when the shield is computed is basically sort of the question I'm interested in. Like, is this something that happens during, like, at the same time as gradient descent, or does this happen like after gradient descent in the function approximation setting? Or does it even work at all in the function approximation setting?
Yes, it does. And you can use it both. You can use it during training or afterwards. So you have your guarantees as long as you use the shield.
Okay.
As soon as you remove the shield, you don't have any guarantees anymore.
Right.
So if you give the learning agent punishments for unsafe actions, you will of course also learn the safety requirements during learning, but you still don't have any guarantees that no unsafe action will be part of your final policy. So you only have the guarantees as long as you use the shields. But since this is basically for free, so it doesn't cost you runtime, you can just also let the shield there after training and have the guarantees as long as you use the shield.
Right. All right, so some getting into some of the final notes here. If someone wanted to replicate this paper, do you have any advice for them?
So if you want to do experiments, and the shield could really help a lot, then it's cool if you pick examples where you have to do a lot of planning ahead, where you have multi-agent setting, where you have robotics in smart factories or something like this, where you have to think many steps ahead before some unsafe things happens. Of course, you can only use it also for simple invariance properties, but a lot of impact you get when you have to think several steps ahead. Like for example, in Backman, where you have to think how all of the ghosts will move in the next couple of steps in order to pick the next direction to go. And this is typically pretty hard to be learning agent and very simple parts. Because we get this by solving the game, that we really consider all possible future inputs and compute the safe outputs for that.
Okay, interesting. So it's been a while since 2017. What's been going on in shields since this paper was published?
We extended this work in several different directions. We considered, first of all, different specification languages. We considered timed automata specifications, so that you can synthesize shields for real-time systems where you have complex timing constraints that can be enforced by the shields. As mentioned before, we went into the probabilistic setting, where you say, okay, I can't always guarantee safety for sure. I can always only give probabilistic safety guarantees. Or you also test things like in the beginning, during training, I want to allow the learning agent to take some risks, and then as learning progresses, I get stricter and stricter and stricter. And we wrote a paper where I can do that on the fly. We wrote 2 papers where I say you can compute the shields online. So if you notice that your environment changes and the models of the environment that you have don't fit anymore, then you update your model, you repair your model, you refine your model, and then from the new models that you get, compute a new shield on the fly and immediately use the new shield. Yeah, so there are several papers that we wrote in the last 2 years that extend the initial work.
Very cool. Yeah, so this has been. I really enjoyed reading this paper. I'm really interested in the work, and this has been a really exciting interview. Is there anything else you'd like to get out to readers of this paper?
Perhaps, Bettina, allow me to take this one.
Sure.
So what we did in the paper was to combine ideas from formal methods with ideas from reinforcement learning. And we had a very clear separation here. To make sure that the system behaves correctly, we use concepts from formal methods. And for making systems perform well in practice, on average, we use reinforcement learning. And I think all of us think that this combination makes a lot of sense in order to get systems not only safe, but also performing well in very difficult control situations. And I think this is like the main message of this paper, that this combination is possible and it can work at least in the examples that we tried so far.
Yeah. What are some barriers or cultural differences that you see between like the fields of synthesis and learning? Is there a do you think like there's more potential than is being seized to combine the two? What's sort of going on into the future there?
That's an excellent question. Let's start with that.
So I think it's difficult for the reinforcement learning community to dive into a completely new area because all of the notations that we use are different. So it's, for the community, it's really new approaches they have to dig into. And I guess this is difficult at the beginning. But there were several papers in the last years of triple AI. So I think the connection between formal methods and reinforcement learning and AI in general, like it's getting deeper and deeper with every year.
Mm-hmm. Like learning is generating code in a sense because it's generating a set of weights based on like a cost function and an optimization procedure. Synthesis is generating code based on a description of what that code should do. Right? So I'm thinking like for artificial intelligence, it seems very natural that synthesis would play a big role if it was possible to say like solve MNIST, the computer vision data set by synthesis. Like what would that I'm just kind of spitballing here, but like what would it look like to create specifications to like encroach on the territory of learning as in like cost functions and optimizations? I don't know. Is that sort of an interesting way to think about it or not?
Well, I think your question makes a lot of sense. And this is also something that a different subcommunity of formal methods has been thinking about. So, as you just said, the main problem with tackling MNIST with more formal approaches is that we don't really have a good specification of what exactly the system to be learned should do. However, what we can do in that case is to perform some sanity checks. So, for instance, in MNIST digit recognition, adding a little bit of noise, meaning getting recognition to be robust, it shouldn't really affect the results. And this is, again, a more formal type of specification that could be tackled. But there's still this big gap in between, that in formal methods, we assume that we have a good specification. But typically in machine learning in general, if we had a good specification, we wouldn't perform machine learning. And I think bridging this gap and finding basically some point in the middle where we get the best of both worlds, that's really the holy grail of this whole endeavor here.
Yeah. All right. Well, if nobody has any other comments, I'm ready to close on up. Are there any other comments?
Well, thanks a lot for inviting us to the interview.
It was an honor to be your first interview.
Oh yeah, I super appreciate you coming on to be the inaugural episode. I hope this podcast goes places, and you'll be there. You'll be like, I was the first. We were the first. So yeah, I really appreciate you jumping in on that. My guests today have been Doctors Bettina Könighofer and Ruediger Ehlers. Thanks again for coming on to the show. And we'll see everybody. And thanks for listening. And we'll see everybody next time.
Thanks a lot. Bye.
Thanks a lot as well. Music by Alex Kulik. Thumbnail image by Max Weil.